everyone. I am Dr. Manisha Verma from Acharya Narendra Dev College, University of Delhi. I teach physics there. I have started a lecture series on thermal physics, wherein I have discussed various important topics pertaining to thermal physics. In my last lecture, I started with discussion on thermodynamic potentials. What are the thermodynamic potentials? What is the physical significance of the thermodynamic potentials? How can the thermodynamic potentials be used to derive the very important Maxwell's relations? In continuation of my last lecture, today I begin with the applications of the thermodynamic potentials, or basically the applications of the Maxwell's relations. So, the first application pertains to the very important TDS equations. There are two TDS equations, and now let me derive both the TDS equations one by one. To derive the first TDS equation, let us take entropy as a function of temperature and volume, where temperature and volume both are independent of each other. Then by simple consideration, it can be written as ds is equal to delta S by delta T at constant volume dt plus delta S by delta V at constant temperature dV. Let us multiply this equation by T on both the sides. So we get TdS is equal to T times delta S by delta T at constant V dt plus T delta S by delta V at constant T dV. Now, what is the purpose of multiplying the equation by T? Because we have to derive the TdS equations, and as you can see and appreciate that by multiplying T with ds, we are getting TdS on the left hand side. It means the left hand side we have got. Now we have to manipulate or substitute the Maxwell's relation on the right hand side to get the first TdS equation. For a reversible process, TdS is equal to dq. Thus, we have T times delta S by delta T at constant V is equal to delta Q by delta T at constant V equal to Cv. What is Cv? Cv is the specific heat at constant volume. Also, from Maxwell's relation, we have delta S by delta V at constant T is equal to delta P by delta T at constant V. Call this equation 3. If we substitute equation 2 and equation 3 in equation 1, we would be getting TdS is equal to Cv dt plus T delta P by delta T at constant V into dV. This is called the first TdS equation. This equation is very important and finds applications in many cases. Let us consider one such application. Consider 1 mole of a van der Waals gas which is undergoing isothermal expansion from volume Vi to Vf. We are supposed to find out the amount of heat transferred while this gas is undergoing isothermal expansion. From the first TdS equation, as we have just seen, TdS is equal to Cv dt plus T delta P by delta T at constant V into dV. The equation of state of van der Waals gas says that P plus A by V square into V minus B is equal to RT. If I rearrange this equation of state, I will get P is equal to RT by V minus B minus A by V square. Let me differentiate this equation with respect to temperature at constant volume. Then what will I get? Delta P by delta T at constant V is equal to R over V minus B. Call this equation 2. We know that for an isothermal change, the temperature does not change. That is, temperature remains a constant or dT is equal to 0. Then the first TdS equation becomes, using equation 2, under isothermal conditions, TdS is equal to 0 plus RT by V minus B into dV. Hence, to calculate the heat transferred, we will take the integral of TdS. So, what do we get? We get Q is equal to integral TdS is equal to RT integral dV by V minus B. The limits of integration would be Vi to Vf. So, putting the limits and evaluating the integral, we get Q is equal to RT log of Vf minus B by Vi minus B. So, this was the first TdS equation. Now, let us derive the second TdS equation. To derive the second TdS equation, let us take entropy as a function of two independent variables, temperature and pressure. Then ds would be delta S by delta T at constant pressure into dt plus delta S by delta P at constant temperature into dP. As done before, let us multiply the equation by T. This is done because we are interested in finding out the TdS equation. So, TdS will be equal to T into delta S by delta T at constant P dt plus T into delta S by delta P at constant T dP. Call this equation 1. Now, we know that T into delta S by delta T at constant pressure is equal to delta Q by delta T at constant pressure is equal to Cp. Further, from Maxwell's relation, we have delta S by delta P at constant temperature is equal to minus delta V by delta T at constant pressure. Call this equation 3. Please note the negative sign occurring in equation 3. This is because S, P, T and V are occurring in an anti-clockwise direction. Had they been occurring in a clockwise direction, we would have a positive sign. So, anti-clockwise direction means negative and clockwise direction means positive. Substituting 2 and 3 in equation 1, we get the second TdS equation, which is TdS is equal to Cp dt minus T delta V by delta T at constant pressure dP. So, this is the second TdS equation. This equation is also very important, and to illustrate its importance, let me discuss a simple case. We are supposed to find out the amount of heat transferred during an isothermal change of pressure. If we keep the temperature as a constant, the second TdS equation can be written as TdS is equal to minus T delta V by delta T at constant P into dP. Thus, to evaluate the heat, we have to take the integral of TdS. So we get Q is equal to integral TdS is equal to minus T integral delta V by delta T at constant P into dP. Now here I define a very important parameter in thermal physics called the volume expansivity, or it can also be called the coefficient of volume expansion. Alpha is denotes this particular quantity, and alpha is equal to 1 by V delta V by delta T at constant pressure. Now everybody should note that by default alpha is taken to be an isobaric process. Supposing we are asked to calculate the alpha under adiabatic conditions, then we would be taking entropy to be a constant. Anyways, to obtain the heat, we get minus T integral of alpha V into dP, because delta V by delta T at constant pressure can be written as alpha V. V and alpha can be taken outside of the integration sign, and so we are left with Q is equal to minus TV alpha integral dP is equal to minus TV alpha PF minus PI. It is seen from this result that as the pressure is increased isothermally, heat will flow out if alpha is positive. In case of water, as alpha is negative between 0 and 4 degrees, an isothermal increase of pressure causes an absorption of heat. This is a very important result which is seen experimentally also. Now let me illustrate the importance of the TdS equation by considering one more example. Consider the reversible adiabatic change of pressure. Adiabatic means entropy is a constant. So we have ds is equal to 0. The TdS equation will then become 0 is equal to Cp dt minus T delta V by delta T at constant P into dP. Rearranging the equation, we get Cp dt is equal to T delta V by delta T at constant pressure into dP, or dt is equal to T by Cp delta V by delta T at constant pressure into dP. Now what is delta V by delta T? It is alpha V. So we get dt is equal to Tv alpha by Cp into dP. So this means that in a solid or a liquid, increase of pressure produces only a small change of temperature. Also, Cp does not vary. Hence, the above equation becomes delta T is equal to Tv alpha by Cp Pf minus Pi. It is clear from the above discussion that an adiabatic increase of pressure will produce an increase of temperature in any substance with a positive expansivity, that is alpha is positive, and a decrease in temperature in a substance with a negative expansivity, that is alpha is negative. Now let me move on to the second application of the Maxwell's relation or the thermodynamic potentials, which is very important, energy equations. To derive the first energy equation, let me consider the following. If a pure substance undergoes an infinitesimal reversible process between the two equilibrium states, then we have du is equal to TdS minus PdV. This is from the combined first and second law. Du is the change in internal energy, TdS denotes the heat part and PdV denotes the work part. Let us divide the equation by dV. Then we get du by dV is equal to T ds by dV minus P. U, S and P are regarded as functions of T and V. If T is held a constant, the derivatives become partial derivatives. That is, we have now delta U by delta V at constant T is equal to T delta S by delta V at constant T minus P. Now, because we are actually discussing the applications of Maxwell's relation, we will now use the Maxwell's relation. From Maxwell's relation, we have delta S by delta V at constant temperature is equal to delta P by delta T at constant volume, and we substitute this in the above equation to get delta U by delta V at constant T is equal to T delta P by delta T at constant V minus P. This is called the first energy equation. Why? Because you can see on the left hand side we have U. U is the internal energy, and therefore this is called the first energy equation. Let me show an illustration of the application of the first energy equation. Consider an ideal gas. The equation of state for an ideal gas gives P is equal to nRT by V. If I differentiate above with respect to temperature at constant volume, I get delta P by delta T at constant V is equal to nR by V. Call this 1. From the energy equation, we have delta U by delta V at constant temperature is equal to T times delta P by delta T at constant V minus P. Call this equation 2. If we substitute equation 1 in equation 2, we get delta U by delta V at constant T is equal to nRT by V minus P. What is nRT by V? It is simply P for ideal gas. So we get P minus P is equal to 0, which means that U is independent of V. This is a very important feature of ideal gas. For an ideal gas, the internal energy is a function of temperature alone. It does not depend upon the volume, as I mentioned before in my lectures also, but again here I am reiterating this. This is not so for real gases. This particular property is only for ideal gases. Now let me apply the first energy equation to a van der Waals gas. The equation of state for a van der Waals gas after rearranging gives me equation 1, which states that P is equal to RT by V minus P minus A by V square. Let me differentiate this with respect to temperature at constant volume as before, done for ideal gases, and I get on the right hand side R by V minus P. Call this equation 2. If I substitute equation 1 and 2 in equation 3, where equation 3 is the energy equation just derived, I get delta U by delta V at constant temperature is equal to RT by V minus P minus RT by V minus P plus A by V square. RT by V minus P gets cancelled. So what am I left with? A by V square. This means that T delta P by delta T at constant volume in the energy equation minus P is equal to A by V square. Now from the first and second laws of thermodynamics, I have du is equal to TdS minus P dV. Substituting for TdS from the relation, we get TdS is equal to CV dt plus T times delta P by delta T at constant volume into dV. We then get du is equal to CV dt plus T times delta P by delta T at constant V dV minus of P dV. So just collecting the terms, what do I get? CV dt plus square bracket T delta P by delta T at constant V minus P square bracket dV. Thus du becomes equal to CV dt plus A by V square dV. To calculate the internal energy, I take the integral and I get U is equal to integral of CV dt minus A by V plus a constant. It follows therefore that the internal energy of a van der Waals gas increases as the volume increases while the temperature remains a constant. Now I will derive the second energy equation in a few moments. I hope you understood how the first energy equation can be derived and how it can be used, because without the application part, simple derivation is not enough to understand the underlying concept.